Let me give you a function f that takes the set of rational numbers q and maps it to the set of rational numbers q. Let's say the function f satisfies the following functional equation, where if you take any pair of rational numbers x and y, we have f of x plus f of y, the whole thing over 2, is the same thing as f of x plus y over 2. The game now is to determine all such functions f that satisfy this functional equation. And if it happens to be no functions that satisfy this functional equation, why is there none? So for those who have never seen a functional equation before, a functional equation is, well, an equation relating to functions just like any other ordinary algebraic expressions that you would solve for variables. But here, we instead solve for functions that make the functional equation to hold. So returning to our functional equation, this actually has a name to it, which is Jensen's functional equation, and it is named after the Danish mathematician Johan Jensen. And to begin, it is always useful to try and guess some common functions that are solutions to this functional equation. And clearly, you may quickly see that a constant function f of x is equal to c, where c is a rational number, is a solution. Well, just play around with it by trying different types of functions and see if you can get some non-trivial solutions. And what you will see is that it seems that all functions f in the form of f of x is equal to kx plus c, where c and k are rational constant, do satisfy Jensen's functional equation. And indeed, now we are going to prove this fact. The way that we are going to solve this is first to use a common trait in solving functional equations, which is to shift the function f by a constant, f of 0. And the idea behind this approach is that now we can define a new function g of x is equal to f of x minus f of 0. So that now when you plug in 0 to g of x, you get g of 0 is equal to 0. And also, this is motivated by the fact that if we just set x and y to be equal to 0 in the Jensen's functional equation, it will just give a tautology where 0 is equal to 0. So f of 0 can't be uniquely determined, and the reason is simple. It can be any value, as all linear functions f of x is equal to kx plus c are solutions, as we have just guessed. So changing the equation in f to g, we first rewrite the equation by subtracting f of 0 both sides of the equation. Then based on what we have defined for g of x, we have g of x plus g of y, the whole thing over 2, is equal to g of x plus y over 2. Although this is the same equation with f switched to g, but g of 0 is equal to 0 now. And this is important because now I can set y is equal to 0 and x to be a free variable. Notice that as g of 0 is equal to 0, g of x over 2 is equal to g of x over 2 for all rational number x. We can use this property to actually replace the expression g of x plus y over 2 with g of x plus y, the whole thing over 2. So it has an effect like pulling out the factor of 1/2. And what's nice about this is that after multiplying both sides by 2, we see that g is additive over the rationals. In other words, g of x plus g of y is equal to g of x plus y. This functional equation here is actually a well-known functional equation. That is the Cauchy's functional equation. And I actually made a video about it too, which I will link it at the end of the video. So be sure to stick around until the end. And I'll use the result of Cauchy's functional equation, which if such function g satisfies this equation over the set of rational numbers, then g of x is equal to k times by x, where k is a rational constant. Hence, f of x is equal to g of x plus f of 0, which is equal to kx plus c, where c is equal to f of 0, and it is an arbitrary rational number. So this proves that all solutions to the Jensen's functional equation are in fact the linear functions. But now what if we change the domain and range of the function f to be the real numbers? Well, then f actually needs to satisfy one of the three properties in order for it to have a well-behaved function, namely to have the solutions as f of x is equal to kx plus c, like what we have just derived previously. So this is an extension from the rational numbers to the real numbers, And because the way we solve Jensen's functional equation is by using Cauchy's functional equation, this means that the extension from rational numbers to the real numbers is actually the same as the extension we will do for Cauchy's functional equation, which, like what I've said, f has to satisfy one of the three additional properties, and if you want to see a proof of it, then be sure to click this video on the screen right now.